The topic is weighted Hari inequality on topological measure spaces. And the main point is that this is a multidimensional result. So in my presentation, I'm going to talk about first, briefly, there will be history in the one-dimensional case, and then the problems that people faced when they tried to generalize those results to multidimensional case, and then what happened in the multidimensional case. This is the plan of this talk. The abstract is here. We look at this inequality, which I denoted 1. T is a Hardy type integral operator, and then there are weight functions, measures here, and you can see that there are two summability exponents. One is P, another is Q. So the idea is to cover different relationships between P and Q. The case P less than or equal to Q is relatively simple. The case Q larger than P is more difficult. And this has always been like this. The definition of the operator T will be given below, and it is a direct generalization of what we have on the straight line. And then there will be conditions on the subset omega T of some fixed set omega in a housed of topological space. So in fact, when I say multidimensional, it doesn't mean that X has some dimension. It can be any topological space, and in general, there is no dimension, no notion defined in X. And then there are two measures are given. So in part D, I say that the purpose is to describe, to give necessary and sufficient conditions for this inequality to hold for different relationships between P and Q. And here in the last line, I underline the main difference between my results and what people did before, that I do not assume the existence of a polar decomposition, which was assumed in the papers by Ruzhansky, there was Isirkegenov, and there was Verma, 3 authors in this area, okay? So the one-dimensional case, we in Kazakhstan knew about this type of result since 1970s, and this, at that time, we knew it under the name of Mackenhaupt. But it turned out that before Mackenhaupt, there were 2 Italians. I wrote their names here. Tomaselli, Talenti, they obtained their results in 1969. And then Mackenhaupt improved the proof, but the result was basically the same. And then Bradley extended the proof for the case P less than Q. And then much later in 1980s, Mazia and Rosin, they obtained the result for Q less than P, okay? The whole history is described in this book by Kufner, Persson, Samko. By the way, Kufner has been very active in this area. He wrote at least 3 books and several papers. So the multidimensional results have been obtained much later in 1996. And the question is, what people have been doing for almost quarter of a century, around 25 years. They obtained the same criteria were the same, but they obtained different expressions necessary and sufficient for this inequality to hold. And then they provided different proofs, and there were several applications. In particular, here in Kazakhstan, Mukhtar Tilbaevich was the first to apply this kind of inequality. And all those one-dimensional results have one thing in common. All of them use one-dimensional calculus tools like integration by parts or a full an integral of a full derivative of a function. And also, already at that time, it was clear that the cases P less than or equal to Q and P larger than Q are very different. So this is probably all I have to say about the one-dimensional case. Then in the multi-dimensional case, we have a series of papers. The first result was obtained in 1997 in this paper by Drabik, Heinig, and Kufner. Okay, so what they did is that the result was true for an integral operator on the Euclidean space. And the Euclidean space, they used spherical coordinates in order to reduce the multidimensional case to one-dimensional case. And this was important because recently in the last three papers that I have here, it's by Ruzhansky-Verma. There was one, Ruzhansky-Verma, there was the second paper, and then Ruzhansky-Yeserkegenov. In the last three papers, actually, the setup was very abstract. They used some notions from algebra, from manifolds, but in fact, the trick was the same as in the paper by Drabik. They actually used what is called a polar decomposition. And if you have a polar decomposition, you can reduce the multidimensional case to the one-dimensional case, okay? So in this respect, those three papers were not very different from the one that I mentioned earlier by Drabik and other authors. Then the next paper is this, Edmonds. Actually, it's not paper, it's a big book, okay? So they considered here Banach function spaces. And if we look at special case, what happens when instead of general Banach function spaces, we have LP spaces. In that case, actually, they covered only the case P less than or equal to Q. And I said, as I said earlier, the case Q larger than P is more difficult. Then there was Bandaliev. Bandaliev used, I don't remember the name. He used LP spaces with variable P. Okay, I don't remember how they call it. And again, if we consider the special case for his result, when we specify to just LP, usual LP spaces, again, he covered only the case P less than or equal to Q. So I obtained my result for in the general case when that the polar decomposition is not available, and was happy the whole last year. I was waiting for a grant. I actually applied for a grant this year, and I was happy all this time as I was waiting for a grant and did not publish my result. And then it turned out that Cinnamon, in the meantime, obtained very nice results. He published his result this year, 2022. I'm going to talk about it later. But just for illustration, one example from Ruzhansky and Verma, you can see that on the left side, in the beginning here, this is a multidimensional quantity. This is an integral over a ball. And in the end, also multidimensional quantity. But in the mean, you can see that they applied the same trick that was used much earlier. They actually used reduction to the one-dimensional case. And then here I want to talk a little about Cinnamon's result. What did he do? He reduces a general Hardy inequality on a very general situation on a general measure space to the one-dimensional case. Okay, so what happens is that initially we have some weight functions, some measures, and then he uses a transformation in order to map everything into what happens on the real line. Okay, this reduction by itself is a wonderful idea, and it allowed him to obtain many interesting results. And for example, his framework works both for continuous and discrete cases. Previously, people considered continuous and discrete cases separately. There was, in the proofs, there were some parallel features, similar features, but until now, nobody was to consider both continuous and discrete cases in the same framework. Okay, so this is one benefit of his results. Another benefit is that he, using his approach, he can analyze the best constants. Okay, so this is also a good thing. But the drawback is this. Okay, sometimes it is necessary to obtain the criteria in terms of the original weights and measures. And from his result, from his one-dimensional results, it is impossible to go back to multidimensional results. Okay, so from this point of view, my result still is interesting. So what did I do? As I said earlier, I cover both cases for when P is less than or equal to Q and P is larger than Q. And then, unlike Cinnamon, I use original measures. And later on, I'm going to give an example when one actually needs original measures. Well, this is a simple thing that results by Rozhansky and his co-authors are special cases of my results. By the way, they gave the applications of their results to a number of situations. One is to homogeneous groups. Here I list those applications. Okay, homogeneous groups, hyperbolic spaces, Cartan-Adamar manifolds, and connected Lie groups. Okay, so it sounds very terrifying, very abstract, but in fact, everything boils down to that idea that if you have spherical coordinates, then along the radial variable, everything becomes one-dimensional, and from the point of view of the theory of functions, everything becomes very simple. So here the statement, the statement that we want, if we denote by C the best constant in the inequality, we want to obtain a two-sided estimate in terms of some functional of the measures and weights. That functional phi on the left side, on the right side should be the same. The constants C1 and C2 may be different, but they are allowed to depend only on P and Q. They should not depend on the measures and weights. Okay. So here I describe the conditions on domains. Some of them are very close to what Cinnamon has. For example, the first one, which I call monotonicity, he calls it total oddness. That oddness, if you take any two domains, then one of them is contained in the other. Okay, Cinnamon imposes this condition. Then the other conditions here, I impose this condition to make it more transparent and related to what we have in the one-dimensional case. In the one-dimensional case, we have intervals, we have boundaries of those intervals. So the conditions that I impose here are designed to provide exactly that in the general case. So here, somewhere where, okay, we define a boundary, here a boundary, and then, oops, we define a boundary of a domain omega t, and then for that boundary, we postulate description in terms of some function tau, okay? So the boundaries are required to be disjoint, and then the boundaries cover the whole set omega. It's exactly the same which we have in the one-dimensional case. And then the boundaries are assumed to be thin in the sense that the measure of each boundary is equal to 0. Okay, so all of these conditions obviously are satisfied in the one-dimensional case. But I want to emphasize that they are a little stronger than what Cinnamon has. So here is the definition of the integral operator. This tau. This describes a boundary. Okay. So if I write omega of tau y, it means that this is kind of an interval, which is limited by that boundary, omega tau y. And we here in this integral, we integrate over expanding areas. When y moves out, then those boundaries move out and those areas expand, okay? And there are some technical remarks here, which I would like to omit at this point. So this is the two results, two main results. One addresses the case p less than or equal to q. It's this case, and I said this case is a little simpler. In this case, the two-bounded, the two-sided bound is given in terms of this function. We have to take supremum of this function, and we get a two-sided bound. In the other case, it's here. When q is less than p, then we also obtained a two-sided bound, but now that the quantity b is different, it is an integral of this quantity, of this function, okay? And this is a direct analog of what people have in the one-dimensional case and in those multidimensional papers that I mentioned earlier. So a few words, how did I bypass that? The one-dimensional trick that people used earlier. This is what I did. I discretized the problem, okay? And after discretizing, I, instead of applying one-dimensional tools to integrals, I apply something similar to discrete sums, okay? So this is the trick, and it allows us to obtain results for that general situation that I described. Okay, so this is what I noticed, that after discretization, it's possible to estimate resulting discrete sums by integrals. And one of such lemmas is given here. I have several of them, okay? This is a pretty simple lemma from, you could say, first-year students would understand this, and the proof also, okay? So there are several results like this, and they actually replace those one-dimensional tools that people used before. And the common feature of this theory is that everything what is obtained for t can be directly translated to the adjoint operator t. So, I mean, not directly, the proof can be translated to the adjoint operator. So here, the difference between the previous inequality and this one is that now we consider complements of those domains omega tau x, omega minus omega tau x, okay? So this is kind of standard thing. Once you obtain the result for the operator t itself, it's easy to pass to the adjoint operator t star. This is the formulation result for the adjoint operator. Now there will be a long application to the case when that Cinnamons condition is not satisfied, my condition is not satisfied, and we actually need the bounds for the operator norm in terms of the original weights and measures. Okay, so there are some a short literature review. Before doing that, I want to show you the domain. This is domain. Okay, we take a cone. The cone is limited by two sides. This happens in the n-dimensional space, Euclidean space. Okay, so we take a cone and then we take here concentric balls, and we have two boundaries of those concentric balls, and the area between the circumferences, concentric circumferences, limited on two sides by the size of the cone, this area which I tried to show here with green color, this area is the area of integration. And when those concentric balls approach zero, this collapses to zero, and when they go to infinity, this area expands. Okay, and it is written here. When the circumferences approach zero, that area collapses to zero, and then at infinity it expands. So the first to consider this were these two guys, Batuev and Stepanov. Stepanov is a well-known specialist in the theory of integral operators. Batuev looks like Batuev was his PhD student, so they obtained this result. Then it was improved by Heinig and Sinnemann. Whoops, what's this? It was improved by Heinig and Sinnemann, and a different approach was suggested in this more recent paper by Prokhorov, Stepanov, and Ushakova. It was published in 2018. Okay, now that improvement is strictly one-dimensional. So I'm not following this last paper. I am following this paper. The format will somehow repeat the format that they gave in the one-dimensional case. So there will be a long notation here. Probably I should discuss just the definition of the integral. This is the definition of the integral. What happens here that we cut out of omega this domain, the left side, which is described by the left side is described by this, and the right side is described by this. Okay, it's I showed you the geometry on the previous picture. And what happens is that this domain changes. Okay, the total orderedness or monotonicity condition is not satisfied in this case. Then there is what the case P less than or equal to Q is relatively simple. The criterion is given in terms of this functional. Okay, there is some modification in terms of the domains. Okay, now in order to understand the other case when Q is less than P, we need this lemma. Okay, so what this lemma does is that we obtain some partition of the half-axis from 0 to infinity. The points that are defined here, there are two partitions. One partition is formed by the numbers. Actually, there are two partitions. Okay, one is formed by the numbers mk, and the other is formed by the images of those numbers under the functions a and b. And there is more notation. In particular, this one is taken from the paper by Heining. And finally, I forgot to put here that in the theorem we should have this inequality that Q is less than P. I forgot to put it here. So for the case when Q is less than P, we have this statement. This is the best constant C is equivalent to the maximum of two constants K1 and K2. So this is my plan for the future, and this is why I'm applying for the grant in that competition, which was announced by our ministry. That in addition to the statements about boundedness and about compactness of the operator T, the plan is to study approximation theory. For example, approximative numbers, and then we could add Kolmogorov widths. There are many of them. Okay, so once we develop the approach for some kind of those numbers. It's easy, relatively easy to handle the others. Okay? This is all I have. Thank you for attention.